Everyone, I'm Ricardo Bevilacqua for those who don't know me, and we're here to attend Sanny Omar's PhD defense. Sanny has been in the lab for 4 years. He's all you could hope from a PhD student and even more. Published a lot of papers, he got 2 fellowships, he had to turn down 1. He just was all over the place. It's been a great 4 years, very productive, and so I'm sorry to lose him, but he's done a great job. So. Sanny's.
Okay, well, thank you everybody for attending. So, as you said, I'm Sanny Omar. Thank you for attending my talk on the drag device and control algorithm for spacecraft attitude stabilization and deorbit point targeting using aerodynamic drag. So I completed my undergraduate degree in aerospace engineering at Auburn University 2015 with minors in business, Spanish, and computer science. I enrolled at UF in 2015, where I was awarded UF's Graduate Student Fellowship and the Institute for Network Autonomous Systems Fellowship in the fall of 2015. In fall 2017, I was awarded NASA Space Technology Research Fellowship and the National Science Foundation Graduate Research Fellowship, which I took the NASA one. I've conducted internships at GE Aviation, SpaceX, and NASA Ames. There's a patent pending on the drag deorbit device or D3 technology that I helped develop in the lab. I know we have ongoing collaborations with the Italian Space Research Agency, CIRA, as well as with NASA Ames Research Center to implement some of the controlled reentry technologies that I'll be talking about. So over my time as a grad student, I've published or co-authored 6 peer-reviewed journal publications on spacecraft deorbit point targeting, the design of the D3 drag device, reentry safety analysis, and we have 3 papers currently pending in the works on drag estimation, D3 attitude dynamics, and ground targeting. So during this talk, I'll be talking about the research objectives and literature review, the D3 hardware and attitude stability properties, the orbit simulation environment, guidance trajectory generation algorithm, navigation trajectory tracking algorithms, a little bit about the planned D3 CubeSat mission, and some conclusions and future work. So the research objective, it stems from the fact that most low Earth orbit satellites are CubeSats and thus don't have thrusters and are re-entering the atmosphere in random locations relatively and uncertain times. These satellites, if they stay in orbit longer than they need to for their mission, they pose a risk to other satellites. And if they have some components like tungsten or titanium that might survive re-entry, they can pose a risk to persons or property on the ground. An example of that on a larger scale was Skylab. When NASA re-entered the Skylab, they actually tried to use a bit of difference aerodynamic drag to do some coarse re-entry point targeting, but they didn't do a perfect job, and it actually re-entered and sprayed debris all over Australia. Luckily, nobody got hurt. But it's those kind of cases that motivate the need for this type of work. And this kind of thing has become an increasing concern with the recent increase in the number of small satellites. And it's expected as you have more satellites launching, more capable, stronger components, probably the restrictions will become greater and it will be more necessary for satellites to take debris mitigation more seriously. So to address these problems, we've developed this retractable drag deorbit device, or D3, that not only expedites the orbit, but because it's retractable, you can actually modulate the drag, and that facilitates orbital maneuvering, active collision avoidance, and re-entry point targeting. So I'll be talking about the targeting algorithm, which utilizes that drag modulation to actually lead the satellite to a desired deorbit location, and that includes guidance trajectory generation, navigation, and guidance tracking components. And finally, we'll talk about the 2U CubeSat to test the drag device and control algorithms in orbit. So a brief literature review. There's a handful of other drag sails that have been developed. The majority of them that you see on here are single deploy drag sails, just designed to expedite the deorbit of the CubeSat. Of course, with those single deployed sails, you can't perform any active orbital maneuvering. And they also have the issue that they generally are kind of a symmetric configuration like this, and you don't get any control about the roll axis. So a lot of them, some that have launched, have actually started spinning. And the D3 has a way to mitigate that, we'll talk about. The Irene and ExoBrake are 2 drag devices that are designed to be retractable. Irene developed by CIRA that Alberto is working on, Exobrake by NASA Ames. Both of these groups were actually collaborating with them. They're also interested in attempting to perform controlled spacecraft reentry, but as of yet, nobody to my knowledge has done that with complete success, using only aerodynamic drag. So some other reentry point targeting algorithms. There's one by Dutta that you give the orbit initial conditions to post 2 on NASA's numerical optimizer, and post 2 calculates 7 discrete ballistic coefficient changes needed to deorbit a desired location. But that's kind of a black box optimizer. It doesn't take any orbital mechanics insight into account. So the computational intensity and convergence rates may not be as good as an algorithm that actually has some insight into the orbital mechanics problem. An algorithm by Virgili, where it uses an analytical solution to directly compute a guidance trajectory without orbit propagation, but the result is that the guidance trajectory may be less accurate than one that is computed with a high fidelity orbit propagator. Finally, an algorithm by Patera that looks at changing just the ballistic coefficient during the final deorbit phase to reduce casualty risk, but not a precise controlled reentry. So the key contributions I hope to make in this work is the aerodynamic reentry point targeting algorithm with guidance trajectory generation capable of running on board a small satellite, and a robust tracking algorithm to follow the guidance trajectory. Then also a robust and reliable D3 hardware implementation that we can use to test these algorithms on orbit. So I'm going to start by talking a little bit about the D3 hardware and the attitude stability, and then we'll move to the orbital analysis and discussion of their targeting algorithms. So the first place to start is with the old paddles drag sail design. This was developed in the lab before my time, an origami folded drag sail that has a rotating shaft. As the shaft turns, it unfurls the drag sail. The issues with the design, it didn't provide passive aerodynamic attitude stability. It can be difficult to determine the exact sail geometry because you have these complicated folds. And the deployment mechanism still needed some refinement. Sometimes it would snag along these deployment rails. So the second generation device is this D3. The D3 is designed to attach to an existing CubeSat, and as a benchmark for the sizing, we wanted it big enough to deorbit a 12U 15 kilogram satellite from 700 kilometer orbit in 25 years. That comes to a half meter squared required drag area. As you can see, this graph shows orbit lifetimes of various satellites with and without the D3. For your average, say, 3U CubeSat, if you don't have a D3 and you want to deorbit in 25 years, your max altitude is about 600 kilometers. With a D3 equipped on the satellite, you can push that maximum altitude to 800 kilometers. Or if you are at 600 kilometers, you might deorbit in only 1 year instead of 25. And as I mentioned, the D3 big selling point is that it's retractable, facilitates re-entry point targeting, orbital maneuvering, and active collision avoidance. Okay, so I won't talk too much here about the collision avoidance algorithm, but I did want to make this point that when you deploy a drag device, just because of conservation of energy, the product of orbit lifetime and drag area is going to be a constant. So if you want to reduce your orbit lifetime by a factor of 10, you have to increase your drag area by a factor of 10. And if you assume that the collision risk on orbit is related to the cross-sectional area, approximate assumption, your drag device may not reduce the risk as much as you would think, right? Because, okay, you reduced your orbit lifetime by a factor of 10, but maybe you increased your collision risk per unit time close to a factor of 10. But with the D3, the fact that it's retractable means if you see a collision coming, you can actively modulate the drag to avoid that collision. And in that case, you can even reduce your collision risk per unit time, maybe even less than that of the base satellite that didn't have it moving. And these graphs show for a 2U D3 equipped satellite, nominally in max drag, if you get a collision notice, how much you can miss that collision by. So even in the higher 600 kilometer orbit where density is less, even with only 1 day advance notice of the collision, you could achieve a miss distance on the order of 10 kilometers, which is more than enough. Or at minimum, pull your booms in at the time when you approach the collision. So very good selling point of the D3. So the D3 design itself consists of 4 retractable, independently actuated tape spring booms. Essentially, they're like motorized measuring tapes. 4 centimeters wide when fully deployed, 3.7 meters long, and they'll be inclined at a 20-degree angle relative to that XY face of the CubeSat. And that dart configuration is what gives it that passive aerodynamic attitude stability property that we didn't have with the old drag device, and is why we moved to this design. And so the booms can be collectively deployed or retracted to modulate the total amount of aerodynamic drag, which, as I said, can be used for re-entry point targeting, collision avoidance, swarm maintenance, orbital maneuvering. Another cool thing that you can do, you can actually partially retract 2 of the booms that are opposite each other and leave the other 2 booms fully deployed, and that gives you a clear minimum moment of inertia axis that acts as a gravity gradient boom. And then gravity gradient torques will work to align that axis pointing at the Earth. So your roll control can be established using those gravity gradient torques, and then with the aerodynamic stabilization and the aid of embedded magnetorquers for attitude rate damping, you can get full 3-axis attitude stabilization with this unit. So D3 interfacing, we have this D3 adapter stage that connects a D3 device to the actual host CubeSat. And that adapter stage also hosts those blue brackets that have the magnetorquers wrapped around them. D3 consists of 4 deployers. Each deployer, there's an expanded view, requires 2 wires for the motor, 4 wires for the rotary encoder that measures boom deployment level. The way this device works, it has a motor that fits inside a sleeve. Motor shaft pokes out. As the motor shaft turns, that turns this drum. Boom is attached to the drum, so the drum turns, the boom unspools. As the boom unspools, it turns this silicone encoder, which turns the encoder shaft and the encoder wheel, and this rotary encoder picks up how much that encoder wheel has turned, and that way you get a precise measurement of how far the boom has deployed.
That's a quick question.
Sure.
Is the magnetorquer embedded in the tape measure, or I'm confused?
The magnetorquers are embedded in these blue brackets. You can kind of see this like reddish right here.
Magnet wire.
That's a magnet wire. So there's 4 brackets, identical ones underneath this. So you got one magnetorquer wrapped around the Z, one wrapped around this way, and one.
Okay, so that blue box is essentially just a magnetic torquer unit.
Yes, and it also doubles as a structural interface adapter to physically interface the D3 with this existing. This is a Clyde Space CubeSat structure, so that enables them to like mate together. And I have some more, I think, expanded views of that. You can see the magnetorquers better coming up here soon. There's some expanded ones of the D3 deployer itself. There's a physical prototype. We actually have the prototypes in the lab. I can bring them later if anyone wants to see.
Now, since you showed a little picture, I sorry to interrupt. Is that the tape on the top left corner? Top left corner?
Yes.
So is it really flat, or it has a profile?
Yeah, it actually has a bend, just like a tape measure. And the way we put that bend in there, we have 3D printed plastic dies that so the boom, it starts out flat when we order it, and we pull it through those dies, and that puts the bend in it.
Okay.
And that bend is necessary to give it stiffness. Otherwise, it just flops around. In the CAD model, we just made it flat. But the actual thing has a bend. When we're done here, I can grab the thing from the lab down the hall. If everyone wants to see.
I'd love to see it.
Yeah, it's kind of cool. We're proud of it. Do you want to grab it?
Yeah, we keep going.
Okay. Yeah, it should be either on the table or in its Pelican case. So the only active control that needs to run on the D3 to aid with that attitude stabilization is this power limited B dot D tumble law. So classic B dot D tumble law is a very common one, that the desired magnetic moment from the magnetorquers is a negative gain times B hat dot, or B hat dot's rate of change in the magnetic field vector direction. And this will ensure that the magnetic torque that you generate is always as much as possible oriented away from the angular velocity vector, so it's always reducing your angular velocity. However, sometimes if your B hat dot is large, your requested magnetic moment might require too much power. So a slight modification I've made is that when you get a requested magnetic moment, you compute based on the known resistance of the magnetorque and required current how much power you need to achieve that. And then if the power required is greater than a maximum allowable power, you scale down the desired magnetic moment according to this formula, and that caps you out at the max power consumption. This plot shows attitude dynamic simulation with the max power set to half watt. As you can see, with the high initial angular velocity, it activates this trigger here and caps the power at half a watt and is able to detumble within 12 hours. Do you find it?
Yeah.
So while you get that, I'll keep talking here.
Yeah.
So I'll show here the result of attitude dynamic simulation that I did. And in this simulation, we use aerodynamic gravity gradient torques where we want the spacecraft z-axis, so this long axis, to align with the velocity vector, and the spacecraft x-axis to align with the LVLH x-axis, which is the radial direction. And magnetorquers are used for rate damping. And what we're going to see is that the error converts to within 5 degrees of the desired attitude. And there's a physical device mounted on the flight structure right there. So here's an animation that I made in MATLAB. I used the figure of a rocket because that's what they had available, but use your imagination. What you're going to see happen is detumbling now with magnetorquers. It's going to deploy the booms soon. I think it's just about to deploy them, and this blue axis of the rocket is going to be pointing toward us, aligned with the green. That's the velocity direction. This is the radial zenith pointing direction, so this red axis is going to align with zenith. And you see the same thing reflected in these graphs. The X component of the satellite body frame is aligned with the X LVLH frame there, and the Z axis of the satellite is aligned with the Y component of the LVLH frame. And also, I should mention, with gravity gradient torques, it can be stable in 2 different attitudes with your X-axis nadir pointing or zenith pointing. So what I actually do here is use the magnetorquers to ensure that it stabilizes in the correct way. So if I want my X-axis zenith pointing, I'll put a positive magnetic moment along the X-axis, and then that'll try to align that with the Earth's magnetic field. And then when you get to time in your orbit where the magnetic field is zenith pointing, you know your X-axis is approximately the zenith pointing, so then you can deploy the booms, turn off your fixed magnetic moment. And that gravity gradient stabilizes you, correct attitude. And I've tried that several cases. It seems to be fairly robust, but if it doesn't work, you can pull the booms back in and try again. Benefit of being retractable. All right, so any questions on that one? Okay, I'll move on then to the orbit simulation environment. I have a discussion of attitude dynamics and backup slides, but I'm going to focus on the orbit side more here. And then we'll discuss the re-entry point targeting algorithms. So the orbit simulation environment is a fairly classic setup where your state is Cartesian position and velocity expressed with respect to an Earth-centered inertial frame, or ECI. The way I define my ECI frame, I define it as aligned with the Earth-centered Earth-fixed, or ECF frame at the orbit epoch, and then I assume that the ECEF frame just rotates about the ECI z-axis. And it's a good enough approximation for what we're doing here. The equations of motion are written in state space form and numerically integrated using MATLAB's OD113, or also optionally in-house RKF78, a numerical integrator that I wrote. The Earth gravitational and aerodynamic forces are the predominant ones that affect the satellite, and that's what's included in this simulator. Other smaller effects, relativity, solar, lunar gravity, tidal effects, solar pressure, variable winds, precession nutation of Earth's axis are ignored in this simulator, but the fidelity of the simulator is enough, as we'll see, for high fidelity guidance generation or guidance trajectory generation. And the algorithms that I've developed are set up so that they can use external high fidelity simulator from SDK or GMAT if desired. So the gravitational acceleration is given by the gradient of this potential function. This is discussed in the textbook by Montenbroek and Gill. In that potential function, those C and S coefficients are given by the EGM 2008 Earth gravity model that is specific to the shape of Earth. I use coefficients through degree and order 10 in my work. These V and W are given by the following recurrence relations. The aerodynamic model, acceleration due to drag, is negative ballistic coefficient times density times velocity relative to the rotating atmosphere squared, where ballistic coefficient is drag coefficient here times area over 2 times the mass. Some other people define it different ways, but this is how I define it. And this V infinity, velocity relative to the atmosphere, can be computed based on Cartesian velocity minus the velocity of the rotation rate of the atmosphere. The density and drag coefficient, by far the biggest uncertain parameters. especially the density. You can have at a given point, say at 400 kilometers, up to factor of 100 difference between the minimum and maximum historic densities. And that's why it's so critical to use a high fidelity density model when you generate your guidance trajectories. Otherwise, you won't have a realistic trajectory. Drag coefficient, if you assume specular reflection, where particles hit each surface and bounce off at the same angle, which is an okay first order assumption. There's higher fidelity models out there, but okay, the first order. You can actually derive the drag coefficient, comes out to be 2 for a sphere and 4 for a flat plate. So this is a little bit just to showcase the level of density variability. The graph at the top shows density at a given point, I think 300 kilometers altitude over time, and you can see between the peak density and the lowest density, very, very large difference, and that again motivates the need for the high fidelity model. Also, these on the bottom show at 2 different dates, the density variability just around the Earth by virtue of being on the day or night side of Earth, different points around the planet. You can see almost a factor of 2 difference in the density at the same time, just by virtue of different location around Earth, also motivating the need for the high fidelity density model. So finally, propagator validation. So in order to validate the quality of my propagator, I simulated from the same initial conditions in MATLAB in my propagator, as well as in the SDK Systems Toolkit high fidelity orbit propagator, which the SDK HPOP includes the solar pressure and the Earth nutation and the tides and everything, third body gravity, everything you can think of. And then what I got is a bit of an orbit discrepancy, but primarily, I believe, in differences in modeling the density or the drag model. So it was unclear whether SDK is considering variable winds in the drag model, whether they're using altitude above the geoid or above the terrain. But the good thing was that those errors were primarily in the along track direction, and because you have this drag controllability, you can actually correct for those errors with slight changes in the ballistic coefficient. So to get this match within less than 6 kilometer drift over 10 days, I had MATLAB ballistic coefficient 0.1, SDK ballistic coefficient 0.115. And what that basically showing is that if you assume the SDK is like the truth, if you generate a guidance trajectory with a MATLAB propagator, you are well within your drag controllability using the guidance tracker to compensate for any errors that are in your propagator. Of course, if you don't like that, you can also use the SDK propagator directly to generate your guidance trajectories. The algorithms are set up to do that.
Is that just the magnitude of the difference between the position vectors, or is that just the along track component?
This is the magnitude of between the position vectors, but it's almost entirely along track. And this is also over 10 days, so 6 kilometer drift over 10 days is not too bad for this work. And again, the main purpose of the work was that trajectory generation and control rather than making a super high fidelity orbit propagator. It just has to be good enough to generate realistic results. Okay, so we'll jump now into the reentry point targeting algorithm itself, which is one of the key theoretical contributions from this work. So the targeting algorithm, as I call it, has 3 key components: guidance trajectory generation, which computes the ballistic coefficient time over time profile and corresponding trajectory to deorbit at desired location. Navigation algorithm with common filter determines the state of the satellite relative to guidance from GPS measurements. And then the guidance trajectory tracking algorithm, which based on the relative position velocity estimate relative to guidance, computes the ballistic coefficient that the satellite must maintain using LQR full state feedback to return to the guidance trajectory. So the guidance trajectory generation algorithm is based on this first assumption that given some numerically propagated trajectory in your high fidelity model that lands somewhere on Earth, it's possible to analytically estimate the change in the ballistic coefficient profile that you need in order to perturb that trajectory such that it deorbits where you want it to deorbit. And we'll talk about how we'll do that in a second. But using that analytical solution with the shrinking horizon and drag work enforcement strategy allows you to generate a guidance that ends up being a trajectory propagated in that high fidelity environment. And the way that's done is you compute the analytical profile, propagate the trajectory, it'll deorbit somewhere. You take the first portion of that trajectory, and as you see here, that's the first part of your guidance trajectory. You use the remainder, compute another analytical solution to correct the actual versus desired deorbit location, propagate again, take another portion of that trajectory, and you keep doing this cycle of analytical solution, propagate, until you converge to a trajectory that deorbits to within a specified tolerance of your desired deorbit location. So that's fundamentally how it works. So let's talk about how we get to that analytical solution. So the goal is to control the deorbit latitude and longitude at a given geocentric altitude, and the final time doesn't matter for this algorithm. And so the control parameters are going to be an initial ballistic coefficient, a second ballistic coefficient, and a swap time at which you switch from CB1 to CB2. And then also after a certain semi-major axis and a certain terminal time, it maintains a predetermined drag profile. Those control parameters are what the analytical solution has to play with. And what we're going to see is that variation of these three parameters, given enough time, is actually enough to target any deorbit location with latitude below the orbit inclination. Some of the assumptions that the analytical solution is going to use to make the math easier will assume circular orbit around a spherical Earth, density a function of altitude and function of semi-major axis, and the deorbit point before aerodynamic forces exceed gravitational forces. But again, this analytical solution is just used to calculate perturbations from the numerically propagated trajectory. So ultimately, with that shrinking horizon strategy, it eliminates the errors resulting from these assumptions, and your actual guidance trajectory is generated with the high fidelity orbit propagator. So the fundamental building block of the guidance generation analytical solution is this mapping from initial to final state, and that hinges on these two key relations. And that basically says that if a satellite with some ballistic coefficient CB1 takes time T1 to achieve some change in semi-major axis, so some orbital decay due to aerodynamic drag, and experiences an argument of latitude change, delta U during this time, then for a satellite with the same initial conditions and a different CB2, the time and change in argument of latitude are given by these relations. That's a function of the ratio of the new to old ballistic coefficient and the initial parameter value. So for example, if let's say it takes 1 day for the orbit to decay a certain amount, if you double the ballistic coefficient, you double the drag, then it's only going to take you half a day to decay that amount. And the true anomaly you're going to traverse, or argument of latitude you're going to traverse, is also going to be cut in half. And then also this relation, the average rate of change of right ascension for a given change of semi-major axis is independent of ballistic coefficient. So total right ascension change for a given phase of the orbit is that omega dot times the time. And once again, ballistic coefficient here define drag coefficient times drag area over 2 times the mass. So we'll look at the proof for these analytical relations here. I can start from the Gauss variational equations given in textbooks. For a circular orbit around a spherical Earth, eccentricity is 0. There's the only along track force in the FS direction is acceleration due to drag. So you simplify to this relation for dA dt, 2 times acceleration due to drag divided by the orbit mean motion. In a non-rotating atmosphere, acceleration due to drag given by this equation. If you substitute the equations for n and a sub d into the dA dt equation, you get this one right here. Now velocity in a circular orbit is square root of gravitational parameter divided by semi-major axis. So you substitute that velocity equation back into this one. And then you get this second equation for dA dt. You can multiply both sides of the equation by ballistic coefficient and integrate, and you get this result, third equation down the page with the integral. Now if you notice in this integral, remember our assumption that density is a function of semi-major axis. All the changing variables in this equation are a function of semi-major axis only. So when you perform the integral, it's going to be, the result of the integral is going to be some function of the initial and final semi-major axis. And that shows that this delta t times cb quantity, or this product, is going to be a constant for a given initial and final semi-major axis. And that's where this relation comes from, that the delta t cb is constant, so the ratio of ballistic coefficient equals inverse of the ratio of the times. So that's where that first relation comes from.
It's just a constant because you have some given starting semi-major axis and some desired final one?
Yeah, so in general, between some final and initial semi-major axis, yes, that product will be a constant. Under the assumption that density is a function of semi-major axis and the orbit's approximately circular and you don't have other perturbations going on. But to the first order, it's correct.
The changes are slow, so it remains almost circular.
Right. And that's what we'll see in these. The relation is used to kind of derive the analytical solution. And then we'll see the approximation is good enough to actually back calculate the drag profile that you need and then refine that numerically. So, for that second relation, we go about it a similar way. The mean motion in circular orbit is the rate of change of true anomaly, rate of change of argument of latitude. If we multiply this n equals du dt by the inverse of the dA dt equation, we get this equation here for du dA. Again, multiply CB by both sides, integrate, and we also get this delta U, change in argument of latitude times ballistic coefficient product, is equal to this integral, which is also a function of the initial and final semi-major axis. And that proves that second relation, that this product of delta U times CB is also constant for a fixed initial and final semi-major axis under those simplifying assumptions. Okay, so then how can we use that to do something useful? We can use it to characterize the behavior of a new trajectory based on an old numerically propagated trajectory without actually having to simulate the new trajectory. So let's say we've got the satellite initial conditions, we've simulated with some drag profile, and we want to see, okay, if we perturb the drag profile, where does my new trajectory deorbit? And so the way we do that, we divide the new trajectory and the old trajectory into these 4 discrete phases. You can see the dashed line is the new trajectory, and in each phase, the ballistic coefficient is not changing in either trajectory. And so remember that initial trajectory, that's one that's been simulated, so we know the change in argument of latitude, the time, everything at each point. In the new trajectory, we've not simulated that one yet. But so what you can do in each phase of the new trajectory, you can calculate the change in orbital elements, time, right ascension, argument of latitude, based on the ballistic coefficient and the behavior in that initial trajectory. In these equations, subscript 0 indicates a parameter in that initial trajectory, and those I subscripts indicate parameter in phase I. So CB sub I is the new ballistic coefficient in phase I, CB sub I0 is old trajectory ballistic coefficient in phase I. So ultimately, change in orbital elements in time during each phase, you sum all those together, and then you are able then to compute the time and final orbital elements at the deorbit point of the new trajectory, which you can convert that to deorbit latitude and longitude, and all that without having to actually numerically propagate the new trajectory. Okay, so now we're going to think about using that relation to kind of solve the inverse problem. So what we've done, given a drag profile, we can compute the orbit location. What we want to do, given a deorbit location, back compute the drag profile. So to start with, after you propagate that first trajectory and it deorbits some random location on the Earth, you compute the change in argument of latitude and change in orbit lifetime that you'd need in order to get it to deorbit in a desired location. So you have some delta U, argument of latitude change, and the orbit lifetime increase is the longitude difference between that target point and the orbit plane at desired latitude divided by the rotation rate of Earth. So ultimately, you have a desired total delta T sub T, which is orbit lifetime, and a desired delta U sub T, total argument of latitude change. And I'm going to prove this relation here in a minute, but what we ultimately get is that these equations give you the values that you need for the control parameters CB1, CB2, and T-swap in order to achieve the desired total orbit lifetime and total change in argument of latitude based on the ballistic coefficient time argument of latitude during the initial trajectory. And you can compute these control solutions for multiple values of T-swap to explore the full control space. And if you have multiple feasible solutions, you'd want to select the one with maximum orbit lifetime controllability remaining. So we'll talk about here where these come from. So to derive those equations, we'll make the assumption that that swap point between the two trajectories occurs at the same semi-major axis. So what that's going to do, that phase 2 in this graph is going to go away because the swap is at the same semi-major axis, and you're only going to have 2 phases you're concerned about. Phase 1 and then a phase 2 between the swap point and this terminal point. After this terminal point, both are assumed to follow the same drag profile until deorbit. So parameter with a subscript 1 is going to indicate the phase 1 before the swap point. Parameter subscript 2 is a parameter corresponding to phase 2 after the swap point, and those 0 subscripts mean it's a parameter in that initial trajectory. So the total change in argument of latitude, those first two equations, and the time is the sum of the changes in phase 1 and phase 2 before and after the swap point. And those time and argument of latitude in phase 1 and 2 by those other 4 equations can be calculated based on the parameter in the initial trajectory, as well as those 2 key analytical relations that I proved earlier. Okay, so delta U sub t, total argument of latitude change. Some of the changes in both trajectories, you plug in the equations, you can solve for CB1. I'll point with the mouse here. You get this second equation here for CB1. Same relation for the total orbit lifetime to the terminal point. You can substitute the equation for CB1 in here. You get this. Solve for CB2, and you get this relation for CB2 as a function of all these are known. See, all these with the 0 from the initial trajectory, all known, and your desired total orbit lifetime and total change in argument of latitude. Once you compute this, you can plug it in, get CB1, and then update the T-swap to enforce that condition that the swap point happens at the same semi-major axis. Now finally, ensuring feasible parameter changes. So sometimes you might have a desired total change in orbit lifetime and total increase in argument of latitude, but it might not actually be feasible to achieve that. You might not have sufficient drag controllability. So what the algorithm will do, it'll always try to achieve the argument of latitude change, and it'll try to get as close as possible to the orbit lifetime, based on calculating these bounds in the minimum and maximum orbit lifetime given by these equations. And what this is doing here comes from the concept that if you want, let's say, to maximize the orbit lifetime for a given total change in true anomaly, you'd want to spend as much time as you can at the higher altitudes because the orbital period is longer. So for a given number of loops around the Earth, it takes more time. But if you want to minimize orbit life for a given total argument of latitude change, to minimize it, you would want to spend more time in the lower orbits where the period is shorter, so lesser amount of time for a given total number of loops around the Earth. So that's what these equations are coming from. And again, that lifetime change is critical if you want to adjust the cross-range errors of your deorbit point. So a little bit about the single-stage targeting algorithm that we actually used on the Ames TechEdSat 6 satellite when I was there 2 years ago. So in some cases, you might not care as much about longitude error, and you may only want to correct your long-track error. And so in that case, a simplified version of the algorithm, you can just calculate the change in argument of latitude that you need to the deorbit point. And so any multiple of that plus 2n pi is also going to be valid. So you can compute with the analytical solution the landing location for all valid delta U values. Select the one that gives you the lowest total error, and you can compute the perturbed ballistic coefficient needed just by that relation. And you can still do that refinement process, picking a ballistic coefficient, propagating, analytical, propagate until you arrive at one that works and arrives you at the desired landing location. And as I said, we actually tried to do this on the satellite that was on orbit. It was orbiting with the exobrake drag device, and I came up with this simplified trajectory to maintain a single ballistic coefficient all the way to the ground. And we actually got the satellite to within one orbit of the desired deorbit location. It overshot, but the reason it overshot was because the satellite didn't stabilize the way they hoped, and it started tumbling end over end. So between their commanded minimum and maximum drag, there was a very, very little difference. So there wasn't sufficient controllability. But I think if we had enough drag controllability, we might could have hit pretty close to the target location with this process. And that's about the simplest way that you can do things. Another added part of my work, the drag work enforcement strategy for the guidance generation. This is something that I found helps with the convergence rates to reduce discrepancy between the analytical and numerical solutions. And the way that works is during the orbit propagation, you can compute the total work done by aerodynamic drag as a state variable. in your numerical integration. So for your original trajectory, you have total work done by drag at each point in time. And then you can analytically calculate for that analytical trajectory what the work done by drag should be at each point in time, according to your analytical relations. And as you propagate that trajectory, you can actually adjust the ballistic coefficient to ensure that the actual work done by drag is equal to the work done by drag prescribed by the analytical solution, and that helps reduce discrepancy between your analytical and numerical orbital solutions. The way you actually calculate the work that should be done by drag is based on that assumption that at those black dots, the start and end point of each phase, the total work done by aerodynamic drag is the same between the new and original trajectories. So if you have some new trajectory at time delta t beyond the phase endpoint with some ballistic coefficient, the time after the start of that corresponding phase, an initial trajectory with the same energy state is given by this relation, ratio of the ballistic coefficients times delta t. And so the total work done by aerodynamic drag in the original trajectory at time t0 after the phase is equal to the work that should be done in the new trajectory at time delta t. So for example, let's say you're in phase 3 and you are 3,000 seconds beyond the start of phase 3, and you've got some ballistic coefficient that's twice the ballistic coefficient that the original trajectory had during that phase. So you're doing work by drag twice as fast. Your work at t equals 3,000 is going to be equal to the work done by drag in the original trajectory at t equals 6,000 because you have twice the ballistic coefficients. That's basically what that is. That helps the convergence rates a lot. So now a little bit of sensitivity analysis investigating the effects of changes in parameters on the drag profile and the deorbit location. And I showed this to motivate the need for feedback control in the guidance tracking, which I'm going to talk about in a little bit. And as you can see, especially in those higher orbits, 300 kilometers, even a fraction, a quarter of 1% of a change in the ballistic coefficient results in the satellite landing all the way on the other side of Earth. And because of the uncertainties in the drag coefficient and the density, even with the best orbit propagator, it's a hopeless attempt to just try to apply this open loop and expect it to land where you think it's going to land. Motivating the need for feedback control to make sure you stay on your guidance trajectory. So to do that, we perform full state feedback guidance tracking using the Schweigart-Sedgwick equations of relative motion. They're similar to Closey-Wilshire equations, but they include the effects of J2, so slightly more accurate. And those will basically give the behavior of this RRL over time, which is the position and velocity of the spacecraft relative to the guidance trajectory. These are linearized equations, so it makes a ripe opportunity for a use of a linear quadratic regulator to drive the relative position velocity to zero. So those up there in plane, Schweigart-Sedgwick equation, we don't care about the out of plane direction. So X will be your radial error, Y is your long track error. For the purpose of the controller, your control is this delta CV between the spacecraft and the guidance. Again, linear state space equations, right for use of LQR control. So the commanded spacecraft ballistic coefficient, according to this control logic, is going to be the guidance ballistic coefficient minus LQR gain times that in-plane 4-element state relative to the guidance. That gain matrix can be computed solving the Riccati equation using MATLAB's LQR command, where the LQR gain is the one that minimizes this cost functional that's based on the control effort and the state error over time, where Q and R are user-defined weighting matrices. R is a penalty on control effort, Q is a penalty on the state error. So now how do we select the Q and R matrices? That's one of the hardest things about LQR control. Often there's not a straightforward way to set those Q and R matrices. So the way we do it here, the way that I found works well, for the Q matrix is to only have that one in the second element of the diagonal, everything else zero. So what that's going to mean that the system is only going to care about minimizing error in the along track direction. However, in the orbital mechanics, if you have a radial error, eventually that's going to translate into an along track error. So in the attempt to minimize the along track error, the system is going to implicitly also minimize the radial error as well as the error rates but it will allow radial error to temporarily grow if necessary, if it needs to do that to minimize a long track error. And that is actually necessary because if, say, you're out of phase between you and your desired orbit, you have to generate some radial error to be able to perform that phasing maneuver. So this Q seems to work very well. And so now we're left with setting the R matrix, which is essentially how aggressive you want the controller to be. And to kind of have a more intuitive tuning parameter for the R matrix, or the aggressiveness of the controller, we defined this delta Y sub sat variable, which is the desired along track separation at which your controller is guaranteed to saturate. So to enforce that saturation condition, based on delta Y sat, you need a certain value of that second element of the LQR gain matrix. And what you can do is first compute the LQR gain with the arbitrary initial R matrix, R0. And then you can update R based on the square of the ratio between the actual value that you got for the second element of K and your desired value of K to enforce a saturation condition. So you update R, then you can compute the LQR gain once again with that new value of R, and it will enforce that saturation condition. And you can also recompute LQR gain periodically as your density changes, and because density changes will result in that B matrix changing.
What's the saturation? You mean your boom is fully extended and you can't go further?
Right, or fully retracted.
Okay.
No. Yes, that's what I mean. And so that's this saturation. So if your nominal trajectory was, let's say, minimum drag configuration, saturation would be like commanding all the way to go to max drag. So it forces that condition, and that just kind of provides a little bit more intuitive parameter for tuning the aggressiveness of your controller rather than just a number for R. And so if you set a lower delta R sat, the controller is going to be more aggressive. So tracker here, simulating the guidance tracking, this yellow trajectory in the graph on the right, that's a guidance or drag profile or CB profile for the guidance. So I simulate the tracking of trajectory, and I just multiply all of the densities by a factor of 1.5, just a bias error. And so if that results, the drag force ends up being too high, the satellite gets ahead of the guidance, the LQR controller sees that the satellite is ahead of the guidance, and it automatically drops the ballistic coefficient to keep the satellite on the guidance. So that's kind of cool because the controller has no a priori knowledge that the drag is off by a factor of 1.5. It's not making any attempt to estimate the drag. It's just feeding back on that relative position velocity that you would get from GPS, and it's able to compensate for that error, keep you on the guidance. And the actuator is only running 0.12% of the time to achieve this. And finite actuation and actuator deadbands are included in this simulation as well. So here's an example of a saturation condition. So I started the guidance in the spacecraft 140 kilometers apart. And as you can see, in an attempt to bring the satellite back to the guidance, I ended up hitting both the minimum and maximum saturation conditions. Saturation handling is not too bad in this controller. If your requested ballistic coefficient is above the maximum, you just set CB equals CB max. If it's below the minimum, you set CB equals CB min. Not every control system is stable when you do that, but in this particular problem, it remains fine to do that. Some more tracking simulation with drag error. In this simulation, I have bias error as well as sinusoidally varying errors corresponding to 26 days. That's the sun's rotation period, 1 day in 5,400 seconds or one orbit. Delta Y sat equals 10 kilometer. And you can see the tracker maintains on the guidance trajectory within 2 kilometers. And all this sinusoidal behavior, it looks like the controller is going unstable, but it's actually not. What it's doing is correcting the ballistic coefficient to match this 5,400 second oscillatory density error. You look at the time scale here. So that's kind of cool. The controller has no a priori knowledge that those density errors are coming, but it's able to correct for them just by virtue of that along track position velocity. So finally, the noise model. Noise based on the PyNav NG GPS unit that we plan to use in our CubeSat. And that GPS unit has Gaussian errors as well as time-varying bias errors on position velocity. The bias errors end up being important to consider because, as we'll see, a common filter can get rid of the Gaussian errors, but it can't get rid of the bias errors. So if you just feed the raw GPS measurements in, the controller stays stable, but you can see it's running 84% of the time trying to chase the noise. So that's where extended common filter comes in, improves things a lot. And a slight adjustment of this common filter over the classic theory, I estimate here directly the in-plane position velocity relative to the guidance, instead of estimating the absolute Cartesian position velocity. The benefit of doing that is because that in-plane relative position velocity is governed by those Schweikart-centric dynamics. You can derive up here analytically approximate state transition matrix. And then when you do your estimate phase of the common filter for predicting the state at the next point in time, I do a full nonlinear orbit propagation. But then for the covariance matrix propagation, I use this analytical state transition matrix. And then for the update phase of the common filter, your measurement Z is raw GPS position velocity converted to relative in-plane position velocity. And that works quite well. You can see relative to that previous trajectory, 84% of the time running versus only 0.43, so over a factor 100 improvement there with the common filter removing that measurement noise. So this is a tracker simulation with everything considered, sinusoidally varying density errors, noise, tracking all the way down to 90 kilometer altitude, 5% actuator deadband, finite actuation time, 4 minutes to go from CB min to max. And you can see it still keeps on the guidance trajectory within 4 kilometers. Actuators running about 3.5% of the time in this case. So very good performance. Finally, did some Monte Carlo simulations to verify the guidance and tracking algorithms. So 1,000 simulations with randomized initial conditions, different ballistic coefficient ranges, different epochs, different target locations, ran a guidance generator, guidance trajectory generator for each of those cases, and then simulated tracking of each of those cases. And all of the guidance trajectories converged. 997 of them converged below the 25 kilometer threshold that I set, at which it stops trying to improve it. Even the 3 that were above that, all were below 106 kilometers on the guidance. All tracking errors were below 6 kilometers. All 1,000 runs. So a little bit about here, how do you actually select the deorbit point that you want to target if you're interested in landing the satellite at a point on the ground. This is what I'm working with Alberto on. What you can do is start in a 140 kilometer circular orbit, simulate the trajectory until ground impact, figure out the argument of latitude and right ascension change needed to adjust the trajectory such that the landing point is on top of that target, update the initial conditions, repropagate again, and keep doing that iterative sequence of estimating the right ascension, argument of latitude change, updating, repropagating, until you arrive with a trajectory from that initial 140 kilometer orbit that lands in the ground point. You take that trajectory, take the point at 120 kilometers or lower if you want, geocentric altitude, and that's your deorbit point. You run then the classic targeting algorithm that I discussed to hit that point. And then you can update the ballistic coefficient just in the last part of that trajectory a little bit if desired to reduce any remaining along track errors. So re-entry safety analysis, this is some work I did with a visiting student a couple of years ago. We looked at the dispersions on the ground, assuming you take a satellite here in this case to 120 kilometers and leave it uncontrolled. And what we basically found is that if you can have your satellite controlled to around 125 kilometer altitude, then your debris dispersion is small enough that you can fit it within this South Pacific Ocean uninhabited area. So this is important if you're doing a shallow reentry of the spacecraft just for debris mitigation purposes. Okay, so our last few slides about the D3 CubeSat mission.
Hey, Sandy, question from Jed.
Yes.
What's driving the clustering in that previous set of data?
The clustering?
Yes.
Well, so the different variables that apply to this Monte Carlo, you had the along track and cross track position errors from the guidance generation, and then other parameters that were varied are uncertainty in the density, uncertainty at breakup altitude, aerothermodynamic coefficients, boom buckling altitude, boom bending altitudes, boom melting altitudes. So a number of those different parameters, and it's maybe what you're getting at. The black dots were with only the guidance errors, guidance and tracking errors, and then with the green dots, that's when you include everything, so you have a little bit
You
bigger.
may be asking why there's 3 different groups.
Oh, why there's 3? Oh, we just had different target deorbit points just to see what happens when you have a different deorbit point that you aim at.
Okay.
Yeah, sorry, and sometimes it'll affect it largely because you have that equatorial bulge of the Earth. So if you're kind of, let's say you're above the equator flying south into the equatorial bulge, you'll hit the higher density more quickly, so you'll have a smaller dispersion. But let's say if you're in the southern hemisphere flying south away from the bulge of the Earth, it will take you longer to hit that high density region, and so you might end up having like a larger dispersion. So it's not always identical at every single point. So I think that's why we do this.
Okay, thank you.
Yep. So just a few quick slides here on the D3 CubeSat mission. I won't go into too much detail, but that's the CAD model of everything we want in our CubeSat, and you can see the prototype right there on the table. We use COTS parts whenever possible to minimize risk. The things we're building in-house is the D3 flight computer board. Tanya's helping with that one. D3 adapter stage, magnet orbiters, magnet orbiter brackets, and the physical D3 device. There's some more views here. You can see a better view of the magnet orbiter brackets on this image on the left, as well as on the physical device. That black D3 on the right, that's the one flight unit that I built for Ames this past summer that they're actually planning to fly on one of their upcoming tech ed sets. A few more views of the CAD model, including custom solar panels that we had to get made there on the left to allow the booms to deploy. So future work in this research is refining that ground targeting algorithm where we pick a point at 120 or maybe a little bit lower altitude that we want to target with the algorithm such that we get a desired ground target. And we're currently in the process of that, and hopefully we'll have a paper out on that by the end of the year. Gordon and I are working that. As Jeb's mentioned, D3 flexible body attitude dynamics, that should be taken into account in future analysis because it could have a significant effect, especially with booms that long and that thin. Eventual implementation potentially of the ground targeting algorithm on the Mistral and Hyperdrone satellites using the Irene heat shield as the drag device. That's something that Alberta is working on with CHIRA, Italian Research Agency. Completion and launch of the D3 CubeSat at the University of Florida, flight of the D3 unit on the Ames TechEdSat CubeSat. So in conclusion, we see that targeting a reentry point using solely aerodynamic drag is indeed possible using guidance trajectory generation, guidance trajectory tracking and navigation algorithms that I've discussed. Algorithm reliability demonstrated via Monte Carlo simulations and case studies. We've developed a retractable drag deorbit device to provide attitude stability and facilitate reentry point targeting. D3 CubeSat in development at UF to test the drag device and algorithms, and ongoing collaborations with NASA Ames and the Italian Space Research Agency to use the hardware and algorithms for reentry point and ground targeting. So there are some of my references. Take any questions.
Thank you, Sandy. Thank you very much. So we'll give the audience a few minutes before the committee goes closed doors and we ask our questions. Comments, questions?
Yes.
On your slide with the Monte Carlo simulations that you had, where you had the table of all the different properties right here.
Yeah.
How did you pick inclination of 1 to 97? What's the significance of that interval?
So the 97, that's inclination for sun synchronous orbit. So the majority of satellites will be between 1 and that. If you go more than 97, you're launching in a retrograde orbit, and usually that's not desired. You want to launch in those lower inclinations to take advantage of the Earth's rotation. So that's kind of a popular range.
Is there a reason that 0 was not in there? Or
So like some of the orbital elements become undefined when you get to equatorial orbit. And the other thing, if you're in equatorial orbit, all your target locations have to be at 0 latitude.
Okay.
So and there's not a ton of low Earth orbit satellites in equatorial orbits. but but you could totally run it for a bigger range if you wanted to. Just figured that was a good representative range. Anybody else?
They're too impressed. All right, if you could give us the room for a few minutes.